guess worry about it if you didn't get the grade you expected. There's still going to be many more opportunities to increase your grade. So plus the test. So I mean, the homework is that what's weighted more anyway, right? So it's like that one's like 57% of your grade. Each test was like 12, so for a total of 24, and then your final. So so I know I think this past test, the one that got you guys the most I saw was the number 3, the orthogonal complements for those two polynomials. So I did. So I remember, I guess when I said so, remember the process of me doing it with just normal vectors. Well, you just literally had to repeat that process, and there was a few people who did. They just repeated the process of number 3 in the review with the integral, and they were able to get that. A lot of so what I saw a lot of people do, which I'm not sure if you guys maybe saw, because it was weird. I'm not really sure if you guys were like doing it, like if you knew what you were doing or not. But basically, what you did was you took the polynomials, you saw the coefficients. I don't know, say it was like 1, 0, 5 or whatever, and you put it in vector form. That's it. So basically what you did right there was you took the coordinates, the coordinate vector of the polynomial, and then just put it as a vector, which is correct. You can do that, and you basically got 2 coordinate vectors. Now the part that you can't do though is, remember how I took the I think it's like 5 or 10, but but either way, you guys will still have more ways to get more points. So yeah, don't worry about that though. Okay, what was it? Oh yeah, that's right. So you guys took the matrix, you put it in the matrix, which we did in the review, took the transpose, and then found the null space of that. So that would have been correct. However, the thing is that while vector spaces are isomorphic to each, like finite dimensional vector spaces are isomorphic to each other, meaning we can go between matrices and like polynomials or whatever, they're not isomorphic as inner product spaces. So the inner product I gave you for polynomials doesn't necessarily transfer over with matrices, but with whatever, however the matrices were over here. So that means that inner product would not have been the dot product. It would have been some like other crazy thing like that you don't know of. Like, well, I mean, you would have to like construct it, but and that's a way above the level of what we're doing right now. And so doing the dot products at that stage would not have been correct, which is why that's why I counted that wrong, because that it no longer becomes you're no longer looking for the orthogonal complement. You're just doing dot products in that respected inner product space, but so they don't match anymore. So, but anyway, that's really the only one I saw that people struggle with. And then number 4, I saw some people struggle with it, but at least I saw that some people did do the correct attempt. So I say like 50-50. I think 50-50 people. Some of them did the correct thing, which was just to notice that for a vector v, I mean, for a vector to be in v and not w means that it can't be written as a linear combination as the span of those 2 vectors I gave you, and then just find conditions on your coefficients, and just, I don't know, just plug in something that breaks it, and then you got it. Some people did that. Some other people I saw used Gram-Schmidt on the Gram-Schmidt process, which wasn't correct either. But either way, point is that don't worry about it. Do the homework for sure. That's basically what's going to give you like a ton of points. And like I said, once I get to it, we'll be doing a homework session. So I'll be holding homework sessions even after the final. So for those of you who want to get more points, we'll be able to do so by tuning into the session up until the end of the grading period, basically. Okay. Okay. Any questions before I move on? Yeah. Yeah. I recorded the last one. I haven't posted it though. I'll record them. I just had to like get this stuff like the grades out. So, and I will. Oh yeah. Also, I'm almost done with the great reports. I just needed to do a little stuff on the on the code until, but you'll get those today for sure. That way you get to see your projections today. Now that I have like basically your test 1 and test 2, along with your homework, you should be able to see the projection. So I'm gonna basically put all your homework there now, along with your, I guess, 3 or 4 packbacks that we did, and your bonus points in your test, and then that will be what you're standing in right now, and with the projections. Yes, I'll be changing the due date. Don't worry. It's not going to be the 4th anymore. It's going to be like, I think what it says, like the 12th or something like that. Any other questions? Okay. So let's finish up the material then. So let's see. All right. So what was the last? Oh yeah, that's right. So the very last thing we were talking about is symmetric matrices and the spectral theorem, right? So yeah, perfect. So oh yeah. If you're graduating, yeah, email me definitely. I mean, anybody here graduated? No. Okay. Anybody in chat graduated? I'm guessing you will be. But yeah, email me if you're graduating. I'll send out an email for those students, because you're right. I have to submit those grades earlier than the, I guess, students who aren't, right? Okay. So let's finish up. It shouldn't take too long. So basically, let's talk about the diagonalizing symmetric matrices. So I talked about how you could ask the question, what matrices are diagonalizable? You can like classify them and which ones are always diagonalizable. And I said those are the symmetric matrices. I.e., so let's just define a few things. If you, so let's define just A is symmetric if A equals A transpose, right? That's what we said the symmetric matrices are. The second thing, a square matrix, let's say, I don't know, P, is orthogonal if I mean, either one of these, PTP is equal to the identity, or you can just say the PT is equal to the inverse of P. It doesn't matter. Either one of these, if any one of these happen as orthogonal. And then let's see. Other thing that I need to say. Okay. And then I guess the third one that is in the book, a matrix A and our square matrix N is orthogonally diagonalizable if, oops, my bad, hold on. Give me a second. This is so fun. Okay, so orthogonally diagonalizable if there exists a orthogonal matrix P such that A is equal to P D P transpose or inverse, it doesn't matter. And I guess I should say and diagonal matrix D such that this is true. So these are the three things we're going to just use. So basically, it just comes down to this. If you have orthogonal a symmetric matrix A, not only could you diagonalize it, but you can orthogonally diagonalize it. Okay. So how do you do that? Well, I mean, it's not much more than what we already know. So do you remember how we diagonalize the matrix using the eigenvalues and eigenvectors? Well, you do the exact same thing, and you just add one more step. Does anybody know what that step would be? If I want to make a matrix P orthogonal, I guess maybe I should say this before I where is it? Theorem 7.3. A matrix P is orthogonal if and only if its columns form a orthonormal basis. Or set, I guess I should say, not basis, set. Okay, now that you know this, what do you think you will do to diagonalize a symmetric matrix? To be, or not just diagonalize, orthogonally diagonalize. So you do the same thing, eigenvalues, eigenvectors, put them in the columns of P, the diagonal D. Now there's just one more step to do after that. What do you think would be? What would make the columns orthonormal? There's only one thing we know how to do, right? To make, if I give you a set of vectors and I told you to give me back an orthonormal set, what would you do? There's only one thing we know, right? Which is starts with a Graham Schmidt. Yeah. So literally you just do that. Do what we did in section 7.2. Compute the eigenvalues, eigenvectors. Instead of, and then once you have your eigenvectors, just you perform Graham Schmidt on it. And then those new vectors you plug into your P, and then your diagonal is the same as your eigenvalues. And then you do that. However, there's one, I guess, warning. You can't just do that with any matrix. It's only with symmetric matrices, right? So before I can even, I guess, ask the question, I guess before I even say, if I ask you, for example, can this matrix be orthogonally diagonalized? You should answer this. You should answer this way. Only if the matrix is symmetric. If it's symmetric, then you can. If it's not, then you can't. So you can't just do Graham Schmidt on it. It won't work if it's not symmetric. Okay. So so we'll do. I'm gonna state one more theorem. Basically what I've been saying. So this is called the fundamental theorem of symmetric matrices. Let A be an n by n matrix, and so A is orthogonally diagonalizable if and only if A is symmetric. So basically, this is what it tells you. Again, I asked you the question, can this matrix be orthogonally diagonalized? You should answer only if it's symmetric. Like so. By the way, that's the last theorem I'm ever going to write in the class, so you don't have to worry about writing anymore. Okay, so let's compute an example. All right, so let's see. Let's do example 3.1. Orthogonally diagonalize, say A is equal to -2, 2, 2, and 1. Okay. First, what should you do if I ask you this question? Check if it's symmetric, right? Is this matrix symmetric? It's not a trick question. It's just, yeah, right. It is, right? Because if you take the transpose, it's going to be the same thing, right? So solution. So you should always say observe that A is equal to A transpose. So A can be orthogonally diagonalized. Okay. So you do the same thing what we've always done. Find the eigenvalues and eigenvectors. So take the determinant of A minus lambda I, right? Which is going to be just lambda plus 2. Oh, sorry. Yeah, lambda plus 2. What am I saying? 2 minus lambda. 2, 1 minus lambda. Take the determinant of this thing. And this thing is just going to be -2 minus lambda. 1 minus lambda minus 4, right? Okay. So from here, you can maybe just see that this is going to be a -2 minus lambda. Sorry, -2 plus 2 lambda minus lambda plus lambda squared minus 4 lambda squared plus lambda minus 6. And then set this equal to 0. So you get that lambda plus 3 lambda minus 2 equals 0. So you get that lambda is equal to -3 and 2, right? So here's your eigenvalues. Yeah, right. You're only subtracting lambda on the back. All right, so next thing we need to do is compute the eigenvalues. So what do we do? Well, we just plug everything in. We get -1. So for lambda is equal to -3. Get -1. Oh, sorry, hold on. No, you get 1, 2, 2, 4. Augmented with 0. You just get 1, 2, 0, 0, 0, 0. So you get that x1 is equal to minus 2x2. So that means that, or v1, v1 or v2. So that means you get x2 times minus 2, 1. So here's your eigenvector. Lambda is equal to 2. So this one you get minus 4 minus, or 2, 2, and minus 1. So this augments to 1 minus 1/2, 0, 0, 0, 0. So you get that x1 is equal to 1/2 x2. So that means you get x2 1/2, 1. But then you can scale the vector by anything you want. So you can say 2 and 1. So this would be your second eigenvector. Okay, so now we have our eigenvectors. So now the only thing left is to take these vectors and perform Grant-Schmidt on it. Okay, so let's see. Oh yeah, sorry. Yeah, what am I saying? It should be 1 and 2. Sorry. Thank you. Yeah, it'd be 1 and 2. Because you multiply by 2 and you get 1 up top and 2 on the bottom. Right. Okay, so by the way, do we have to perform Grant-Schmidt on this? So Grant-Schmidt makes the set of vectors orthogonal. Before you even try to do this, you can just ask, are these two orthogonal? Meaning, if you take their dot product, it's a 0. Well, yes. So observe that -2, 1 dotted with 1 and 2 is just equal to -2 plus 2, which is equal to 0. So they're already orthogonal, so you don't have to perform Grant-Schmidt. The only thing you have to do is make them normal now. So how do you make them normal? Yeah, exactly. So just take this, for example, if this is v1, v2, just let u1 equal v1 over the norm of v1, and then u2 equal v2 over the norm of v2. What is this equal to? Well, I mean, let's see. So you take v1, you get that, take the norm, you get 4 plus 5. So you get 1 over the square root of 5 times -2, 1. So it's -2 over square root of 5. And then 1 over square root of 5. What about this one? 1 over the square root of 5 times 1 over 2. 1 over square root of 5. 2 over the square root of 5. Okay. So now we have them normal. So let P be equal to -2 square root of 5, 1 over the square root of 5, 1 over the square root of 5, 2 over the square root of 5. And then let D equal just the corresponding eigenvalues, right? Oh, another color. Okay, so the corresponding eigenvalues was, I think this one was -3, oops, and 2, so 0, 0. So A will equal P transpose this time, right? Because the inverse is the transpose for a orthogonal matrix. So in this case, you don't have to compute the inverse using the RREF. You can just transpose this matrix and it'll give it to you. Um, but yeah, I mean, that's it. I mean, it's basically what this section was really about. Yeah, so that was basically the last thing I wanted to cover, is that the only, I guess the other thing there is that the spectral decomposition of something, but we're not going to do that because, well, one, uh, I think we basically covered the entire book at this point. I think I went a little bit more than well, usually what they go through, but it's fine. Uh, the only thing I guess you can say is that the spectral decomposition. So I guess if you wanted to find so the spectral decomposition can be written as this. So you see A. So you see how we got these U's right here, the columns of P. Well, basically the spectral decomposition is just going to be lambda times U1 transpose plus or lambda 2 U1 or U2 transpose all the way to whatever, right? Whatever however many you have. Anyway, yeah, we will send it. Anyway, this part right here, so these are the columns of P. These things right here. And then those lambdas are the associated eigenvalues to those vectors, basically. Okay, so that's it. I mean, and then that's basically the spectral decomposition. If someone asks you find a spectral decomposition of something, well, at least for symmetric matrices, you do this, and you can decompose it this way. Anyway, that's pretty much all the material I wanted to go through. Just a few more things, I guess. We'll do review Monday. I'll have a review for you guys soon. I just have to like finish making it. We'll go through it Monday and then maybe Tuesday, because I think the exam, if I'm not mistaken, is. Oh wait, okay. So maybe I'll do one Sunday and then Monday, because I think this exam is. Oh no, 7th, right? The 7th. Yeah, this was the last day of class. Okay. Yeah, Monday, Tuesday. I don't think I'm allowed to. Wednesday's dead day, right? Yeah. Okay. So I can't do anything there. And maybe Thursday or something like that. Maybe mix in some homework session around there, and then you guys will have basically all day the 7th to do the final. And hopefully, which I will this summer, because I don't want to. Basically, I just want to get to my summer break, so I'll probably like grade it either that same day or Saturday, and then I'll give out the final quote unquote grades, but those grades can change if you do more homework until the deadline. And like I said, I'll still continue doing sessions until like, so I'll probably do like, for example, so if I graded everything here, you will have the 9th, 10th, and 11th. So probably these days right here to do more homework sessions, and we'll basically knock all of them out. And hopefully that'll give you enough points to basically what I want is I don't want anybody failing, all right? So I'm basically doing like with everything within my power to you guys not fail. Uh, so yeah, so no failing, okay? I won't allow it. Okay, well that's it. If there's no more questions, then I'll see you guys Wednesday. Yeah. So some of the pack will be extra credit. So so it's part of the grade, and then some of it is extra credit. So there's actually, I think, like 2% of it that's extra credit, or percent of it. So basically, if you do it all, you get 2 extra points on your overall grade. It's basically what's happening there. Or a point, I think, somewhere. That's what I think it would. But yeah. Any other questions, comments, concerns? Of course. Right here. I can just export it here. I'll just So, okay, so sorry here. Yeah, just comment on each post and that'd be fine. They'll just comment like some random things on your post or like LOL or something. I just actually put something there like relevant to the material. Okay, any other questions?